So our next speaker is James Pesca, adopting formal methods in the verification of ARM-based CPU systems.
Right. Well, good morning. Hello. My name's James. I'm from ST in Bristol. What I'm going to talk to you today about is a project we've been doing over the last 6 to 8 months, really to look at how we can leverage formal in the use of our verification and how we can extract some added value. So the title of my talk is Adopting Formal Methods in the Verification of ARM-based CPU Subsystems. But really what I wanted to call it is that, how to sell formal to your manager. So what I want to do really is talk a little bit about value. So I'm going to talk about, the value that you can gain from using formal in your verification methodologies and what we saw at ST and how it's benefiting us. So who are we? Very briefly. So my group in Bristol is the CPU part of a CPU-GPU team in TR&D, and TR&D is like the central R&D organization in ST. What we do is we develop a range of ARM-based subsystems for use in a range of SOCs, so these tend to be consumer, mobile applications. And we split our verification across 3 sites. So we do the system-level functional verification in Noida, block-level activities in Bristol, and all our low-power and DFT verifications done in Grenoble. So like I said, we evaluated some formal tools. So we looked at, in particular, at using Jasper. And we evaluated Jasper on 3 projects. So this is what I'm going to talk about today. So I'll go into more depth on each of these as we go through the presentation. All right, so this is an example subsystem. So I just thought I'd throw this up here to give you guys some idea of the type of thing that we're talking about. So basically what you can see is that the primary component of the subsystem is a big lump of ARM IP. So we take an ARM quad A15 in this example with an L2. And then around that, in the bottom right-hand corner, you've got some debug functionality. Then in the top right-hand corner, you've got some ST added blocks. So these are some sensors, a subsystem control unit, and a clock and reset manager. So I'll tell you about those. Then there's some other little bits and pieces, some asynchronous slices around the edges, and that's it. So we compose that, verify it, and ship it. Okay. So about 8 months ago, this really was our strategy for verifying these things. So we did a lot of unit testing. So this was performed by designers, specifically on bits of IP that ST had generated. And basically what we were trying to do is just answer the question, is this block ready to enter verification? Very straightforward. And what we would do is typically the designer would write a Verilog test bench, run some basic use cases, decide whether or not the block basically works. Does it function? All right. Then it would enter block level verification, so we'd throw away that Verilog test bench. And obviously block level work was all performed by verification engineers. And again, what we're trying to do there is to look at whether or not the block conforms to its spec in isolation from the rest of the subsystem. So we don't do anything with the ARM IP, that's verified as far as we're concerned. But we did all our block level work using constrained random approaches, so SpecMan. So again, typically we'd sit down and write a SpecMan test bench. Okay? Then we take all of these blocks, which we block level verified and stuff, compose them together by hand, integrate them together into a subsystem, and perform various levels of system level checking. So we do some additional checks just with some point-to-point checks, just to make sure that actually we've got the wiring basically correct. And you'd be amazed the number of errors we found, because this was all being hand-stitched, the number of errors we found just by doing point-to-point checks. All right? And then as the testing progressed, we'd look at testing the system as a subsystem. So does the whole subsystem work together? Have we got any inconsistencies in specs, for example? And then finally, we do some benchmarking, look at whether or not we've got the right level of performance. Okay, so that about 8, 9 months ago, that was our verification strategy for these subsystems. So just as a quick straw poll, does that sort of ring true with people here? Do you guys sort of do similar things when you do, in terms of your strategies? Yeah? So a few people sort of, yeah, okay. So what we did is we decided to take a step back from this, right, look at how we could use formal to maybe improve upon some of the aspects of our methodology. So in particular, we did 3 projects, and these were designed to increase in complexity. So as the layers increased, so did the complexity. So we started off with a very simple block, sensor control block, developed in Bristol, very well understood, had a very good spec, and it was a good first case analysis for formal. So we did that, and at the same time we developed constrained random test bench so we could make comparisons. And also just to check that we weren't missing bugs. So give us a bit of confidence that actually, our formal verification was working. Okay, so we finished that, and then we moved on to a much more complicated block, something called Clock and Reset Manager. And what that does really is it provides clock and reset fan-out within the subsystem. And that's also in the context of things like operating point transitions. So when you want to move from low power states to high power states, or retention modes to normal running, that sort of thing, that block handles those kind of timing transitions as well. So the block was developed in Grenoble, and it was quite an interesting case because we didn't really have a functional spec for it. So it's very critical, it's very complex. We had a lot of really good microarchitectural documentation, so lots of schematics. And I mean, what had happened basically, the designer was quite old school. So he designed this by schematic and then coded it in Verilog, and had given us, effectively a bunch of microarchitectural docs as being the functional spec. But it was nowhere written down where we could find, given this functional input, what should actually be the functional response? I mean, what's actually supposed to happen? Yeah? And like I said, it's very complex and very timing critical. All right? So again, develop constrained random test bench in parallel so we can make comparisons and make sure we didn't miss anything. All right? Then we did some point-to-point connectivity checking. So this was at the system level. And really what we wanted to do is we had an aging SpecMan flow that we'd used for years and years and years that was buggy and required a lot of maintenance and didn't really do what we wanted anymore. So we decided to get rid of that and look at using, in this case, Jasper as a nice mature industry counterpart. So why have all this maintenance load when we can boot it and use Jasper? Okay, so that's what we did. All right. Yeah, sure, go for it.
Did you find any improvements before?
Yes, yes. I mean, I'm going to
run a random test just to see if you have covered everything, but did you get any improvements before?
Yeah, well, basically, I'll get onto this, but basically, I mean, a lot of the payoff really was in the reduction in effort. All right. So because suddenly, well, okay, well, I'll come to it in a minute, but yeah, there were some good benefits. Okay, so SCB. All right, very simple block, so I won't dwell on this. What it does is it monitors chip temperature, generates interrupts when the chip's getting too hot. Okay, we picked it because it's very simple. So all it is it has an APB-accessed memory map register file, connects to some thermal sensors, samples them periodically, and generates interrupts when things go over threshold. All right, okay? So it's very simple. So we use Jasper in this case just to check the register interface, the APB interface, the actual functionality, so this min-max and averaging functionality that it has, different sampling periods, and the interrupt properties. All right, so that's kind of what we did. Like I said, there's nothing sort of vastly interesting about that. But okay, so results. Found 3 bugs. A very subtle problem on one of the APB signals, which we incidentally we never did quite crack it on the SpecMan test bench, which was interesting. We never did find the same thing. We didn't quite get to the bottom of why. Actually, it's a good point. It's still an open point. We should try and nail down why we never found that with SpecMan, but fine. One RTL problem, so there was an inverted OR concatenation in a typo in the RTL, and a spec problem as well. So it actually highlighted an issue where a lot of these registers we pinned down as being write clear 1, so you could only clear them by writing 1. We found out actually you could clear them by writing anything to them. Okay, so how valid is this? Well, we didn't expect to find too much wrong. I mean, it was, like I said, a very simple block, and the designer had done a lot of testing. I mean, a huge amount of testing. We've done some previous SpecMan verification, and a lot of it was already tried and tested. So it's pretty good, really, for considering that it had had quite a lot of attention and effort in the past. I mean, it still picked up 3 sensible issues quite quickly. Okay, so one of the things I do at ST is, apart from actually working on verification, is I project manage a lot of verification as well. So one of the things we needed to ask ourselves was whether or not we could actually answer the following questions. I mean, we've done some work with it, but how did it mesh into a project? I mean, can you, how do you track progress? How do you know, whether or not you're over constraining the environment? What about things like bounded proofs from my block? What about all this, we're getting an awful lot of coverage data now. We're getting coverage data from simulation, coverage data from low power analysis, coverage data from formal, and we're looking at this very regularly. So sort of, on a weekly basis, I'm looking at this and directing effort and thinking, there's an awful lot of data to collect and consolidate. So we needed to answer these 4 questions. basically, in the context of the tool that we were using, there's some very good answers. So you can do things like measure out-of-coil coverage to find coverage holes, right? So that's analogous with looking at, structural coverage in terms of simulation. You can look at measuring stimuli coverage to check that actually, in terms of your state space, your cone of influence is covering the legal scenarios, so that the valid scenarios, and that you're not reasoning about scenarios which are completely meaningless. We could also use bounded coverage analysis to check that for properties that didn't converge, actually they were going deep enough in the search space. All right, so you can get answers to those questions. So in terms of the quality of your formal verification, is it giving you good quality formal verification? And also, something that was quite interesting is the Jasper guys are now working on a mechanism for merging results from formal analyses, okay, into other UCDB files. So in the future, maybe what you can do is consolidate all of this coverage into one aggregated report, and then you can use that as the basis for your project tracking and your effort direction. Okay.
Sorry.
Yeah.
On the first one, so you mentioned briefly, how do you deal with the coverage, which measuring the coverage which is inside the cone of influence? Because obviously the cone of influence, you might have several different things within that one cone of within the cone of influence, but determine whether a certain portion is covered or not covered or relevant.
That's a good question. Well, basically what you can do is you can analyze it and look at it very closely. Just thinking how best to answer that. That's good. So what you do really is you look at your cover statements and you ascertain, you try to work out whether or not you think your coverage is actually representative of the system functionality. So have I actually stimulated enough scenarios? But can we have a chat about that? Because that's quite a long, interesting conversation. But I don't want to. I'm just a bit conscious that there's only 20 minutes, so I'm moving pretty quickly.
10 minutes left.
10 minutes. Okay. So clock and reset manager. So this was a much more complicated block. What it does is it generates the clocks and the resets within the subsystem. So it takes very abstract, high-level interface from the SOC, and it generates the clocks and the FANACs within the subsystem. And like I said, it's responsible for doing things like allowing the subsystem to transition between operating points. So, for example, you have to do things like quiesce buses and make sure that the timing of certain bring up and teardown is coordinated very rigorously. So, because of that, it has to conform to some of the ARM sign-off criteria. And like I said, we had some very good microarchitectural docs in the sense that the designer had basically documented his implementation quite well, but it was really difficult to verify against that. I mean, it was virtually impossible because nowhere was it actually stated, given this functional input, you should expect to see this functional output. So we just didn't have that. Like I said, it's very complex and very time critical. So what we did is actually, we used Jasper, but, formal in general, to perform feature extraction. So what that means really is you can, in real time, virtually, you can extract properties about your block, and I'll go into this, that allow you to actually make, sort of reasoned statements. So you can actually then go to the designer and say, look, this is what actually happens, this is correct. You can go to architects and say, this is what happens, is this correct? Right? But come on to this. Then we proved a whole bunch of critical properties using Jasper, and again, developed a spec-mount test bench in parallel, A, to compare the approaches, B, to make sure we didn't miss anything. Okay. So feature extraction. All right. So like I said, we had this real problem, and for a long time, I didn't really know what to do about it because there was no spec for this. It was complicated, and nobody really knew how this should work, or so what should actually happen. So I'd have conversations like this with designers in Grenoble over the phone, and this would be verbal. So the designer would say to me something along the lines of, yeah, James, once command in fires, command ACK, that follows sometime in the future, okay? And then once it falls again, command ACK falls, yeah, sometime in the future. All right, so I've stated it slightly more formally, but so I go, well, what does that mean? What can I, how do I reason about that? How do I make any sense in this? How do I move forward? Okay, so what we did is we used Visualize, again, which is a Jasper tool, to evaluate the range of cycles that the ACK follows. So what you can do is you can write properties, different values of M and N. Okay, you can find the lowest value of M and N for which property holds, right? And then you effectively define a cover item for N-1. Now, what that allows you to do is in real time, so I can be on the phone to the designer and he can say something like, so once command in rises, command act should follow after N cycles, for example. And I can type this in real time. So I can say, right, so here's my SVA assertion. So when command in rises, then that implies that in the next, well, between 1 and 80 cycles, for example, command act should fire. Okay, click prove. Oh, that proves. Okay. Now I can change. I can play with this value of 80 until I work out what the minimum is. Right? Okay. All right. Then I can specify. I can just say, okay, so now just cover the case where if I go one less than this, right, I see the scenario where command in rises, then that implies that between 1 and 79 cycles, command act is low. Okay? All right? So I can prove that, but the key thing is I can do that in real time. So I can be on the phone to the guy, right, and I can do that as we're talking, right, and then I can come away and I can go, okay, right, now I know that this behavior is what the block does, right? So this behavior, I've proved it, okay? And I can take that statement and I can go to the architects and I can say, this is what I've discovered. Is this correct in the context of the wider system? All right? So does that make sense or no?
Why not using line assertion?
Sorry?
Why not using line assertion?
Well, you could do another way of doing it. I mean, literally, I mean, in this case, in particular, I was interested in just finding out what N and M were. So I wanted to bound these properties. So that's what we did. You know, and like I said, you can take that information, you can go to architects and designers, and then, you know, from there you can, you know. But what I'm saying is, from this fog of nothingness, right, you've actually got some facts. Okay, I mean, that's what I'm sort of trying to get to you know, to communicate.
You read minds as well.
Sorry?
You read minds.
Sometimes it feels like it, but no, unfortunately. It would be really good if we could apply four more tools to mind reading. That would be excellent. Okay, how much time have I got, Mike?
A couple of minutes and then some questions.
Great.
4 minutes and questions.
I've only got a couple more slides. Right, P2P checking. Okay, if you guys haven't looked at this, we had a very good experience using Jasper on P2P checking. So, like I said, once everything's verified at unit and block level, what we do is we hand stitch it all together, and we generate effectively a golden reference of the connectivity from some of the project documentation. Okay, so this is very heavily reviewed, you know, and we can take that and feed it into Jasper and get it to actually check that the RTL is in sync with the spec. All right, okay. So the key thing, or the thing I want you to take away from this particular slide is that actually this was a very low effort, high value adding activity. So literally within about a day, we'd got the basic framework of the flow up and running. So that was the day with the help of Jasper. But we've basically gone from, you know, having nothing to actually being able to prove something like about 2,000 properties. Okay. Within the first week, that number had gone up to about 2,511. And then within 2 weeks, we'd proved everything, and we had this flow in place. All right. So it was very high value adding, right? Very low effort. I mean, it cost us in terms of what it's cost me in terms of my time. It was a real win-win, basically. So you know, you guys should have a look at it. Now, I'm told as well, actually, once you've got all this set up, it's very useful in the context of low power, because now you can do things like check connectivity rules when you change power states and stuff, and that virtually comes for free. Okay, so once you've done this, all right. I haven't done that personally, but the guys in Grenoble say that actually that comes virtually for free. So have a look. It's worth a look, really. Okay, conclusions. Right. So I started off with this sort of quite, you know, sort of well, hopefully interesting title, I guess. But what we found is that actually there were some real sources of value adding here. So there are a lot of tangible effort savings, and they stem from the fact that you don't have to build large test benches. All right. So it seems that whenever we do block level verification at ST, it always takes us 6 man-weeks to build a block level test bench. Right. And it normally goes in the same sort of path. Normally, you know, verification engineer gets the spec, reads the spec for a week, puts it to one side. Week 2 has a fiddle, maybe designs, you know, test bench. Week 3 starts implementing some UVM-based test bench. Week 4 tracking bugs. Week 5, it's just about hitting maturity. Week 6, you can start actually finding bugs in the design. Okay, so that's just a sort of a rough heuristic that we observed at ST. It always seems to take us about 6 man-weeks to start building block-level test benches. It'll be interesting to see how that compares to other people in the room. But with Formal, the nice thing is, right, you just hook up a clock, a reset, right, and you start writing properties. So literally, on the afternoon of having started it, you're up and running, you're going. Okay. Second key point is that actually properties can be added incrementally and reused throughout the block's lifetime. So like I said before, what we used to do is we start off, we do our unit level verification, write an HDL test bench, so Verilog typically. Okay, once the block enters verification, it gets thrown away. That effort's lost. Okay, enters block level verification, we write another test bench, completely new test bench, which when the block enters system level verification, right, gets used a bit for regressions maybe, but that effort really is now gone. But actually with Formal, what's nice is that you can capture insight and you can effectively build up this database of properties that can actually then live with the block. All right, so those properties you can embed in the RTL and they stay with the block for its entire lifetime. All right, so that I thought was quite useful. Formal, very useful for reasoning about designs that are not fully understood. So like I said, the kind of methodology is responsive enough to be done in real time. All right, when we've used very heavy program-based approaches, so system Verilog or C-directed tests or whatever, then typically the amount of code that you have to write in order to prove a property or to check an idea is significant. So it's not really something you can do in real time. Whereas we found that actually, Formal was responsive enough to do this in real time. And like I said, check out the point-to-point testing because that for us was a big win, very low effort. Okay. All right. So 3 quick key points on deployment. Designers we found really like using Formal, or in particular liked using Jasper. And the reason for that is because it provides sort of good quality feedback quite quickly. I also found it was much easier to learn than sort of, trying to learn big programming language-based solutions. Okay, so that was quite useful. And then when we tried to deploy it in ST, so one thing we did, or we are trying to do is, first of all, we tried to educate the masses, right? And that's really bad because what you do is you get people really, really excited, and then they go off and they try to use it on their work. And unless you can support a lot of people all using the tool at the same time, okay, then it just dies and it goes away. So actually what we've done now is to build a little group of internal champions, okay, and you kind of pyramid out the deployment, right? So they can support teams that are local to them and then the deployment goes a bit more widespread. All right, and like I said, it integrates really nice and easy into project management type stuff. So
Thanks, James.
that's it.
Quickly, any questions for James? Anthony?
I'm quite interested in what you just said about the building internal champions. I must say that's the approach that I think you should be taking.
Yeah.
But I just wonder how far you've got down that process. You've identified champions, and then how's that spreading to the next generation and the next generation?
It is. It's slow, basically, but it does work because actually what happens is, you're building on very solid foundations. So it's very tempting, like I said, instead of getting sort of 50 people into a room and, giving them a presentation and whipping up this huge amount of excitement, right, only for that to fall apart a week later, okay? We find that actually this is, it is very slowly, it's propagating out. And this was actually kind of the approach that they were doing, they took in Intel in ARM a little bit as well. So some of the guys in Intel in ARM who I spoke to, this is, they tried to educate lots of people, and it worked, and then it's gradually catching on. But it builds momentum, it starts moving quite quickly.
Yeah, coming back to the idea of starting off without needing a test bench, a unit test bench. Did you find much buy-in from the designers? I mean, we've had some experience with getting designers to use the tool as a design bring-up tool rather than, to replace effectively the test bench. And did you find more assertions written embedded in the code?
Yeah, it was. I think people were quite keen to use it, so the designers could see the value, and they were, as I said, they were quite keen to just sort of learn something different, expand their skills a bit. And in terms of embedding assertions into the code, that has taken on a little bit, but I mean probably not as much as I'd like at the moment. But it's coming very slowly, and I mean the arguments for doing it are very compelling. So I think it's quite an easy way, it's quite an easy thing to you know, people can see the advantages, so they do tend to do it. But yeah, generally speaking, if it's presented well, then the designers do seem to be quite interested, and they do grasp it.
Brilliant. Okay, thank you very much, James. Thank you.